Ouais.
Oh. Okay, good. All right, this will give us some extra time for whatever classical issues happened with Zoom before. All right. Are the scribbles appearing? Yes? Okay, great. Okay, so we can go ahead and get started then. Okay, so in the previous week or so, Shahar has been talking about kind of extending our natural spectral definition of expansion from graphs to simplicial complexes. We defined kind of our first type of high-dimensional expansion called local spectral expansion. And Shahar showed using kind of what was called the local to global paradigm or Garland's method. We showed kind of two different definitions of local spectral expansion, one that just required kind of expansion in top level links, and one that required expansion in every link. And Shahar showed through what's called Oppenheim's trickling down theorem that kind of you can use a local to global method to prove that these are actually up to a constant in the size of the dimension of the complex, that these are actually the same. So this week we're going to be moving ostensibly to a new topic, but we'll see in the end that it's actually kind of the same topic, just viewed from a different angle. So last time we kind of generalized spectral expansion by looking at kind of the spectra of graphs underlying links. This time, we're going to look at generalizing spectral expansion through random walks. So we're going to talk about what we call random walk expanders. And I should note that as far as I know, this is a name that we made up. And so if you look in the literature, there isn't like a specific name for this type of expansion that we'll be talking about. I think in the original paper by Dickstein, Dinar, Filmus, and Harsha, they just call them gamma high-dimensional expanders, but there are many types of high-dimensional expanders. So this isn't very descriptive. So we picked maybe a somewhat more descriptive name and are just going with this. So we're going to call these things random walk expanders. But if at the end of lecture you have a better name for these, please tell us, and maybe we'll switch the name. Anyway, let's get into it. So the first thing that I want to cover, we're going to spend actually a while kind of just looking at graphs. We're going to build up some machinery on graphs, and we're going to see how it's possible to equivalently view spectral expansion as some kind of statement about random walks. So step one is going to be random walk expansion on graphs. Random walk expansion on graphs. Okay, so basically we want to find some kind of equivalent way to look at, in this case, two-sided spectral expansion through random walks on kind of the underlying graph. And it maybe shouldn't be surprising. The first thing that you should probably look at is the normalized adjacency matrix, right? Because we've talked about previously in the course, we spent a lot of time on this. Section 2 was entirely about this, and I think it's been brought up a number of times. But the adjacency matrix and the spectral expansion is very closely tied to this random walk on the underlying graph, where you move uniformly from a vertex to a random neighbor, right? So recall that the normalized adjacency matrix, and for simplicity, let's just assume that graphs, so for this kind of section on graphs, I'm just going to assume things are deregular. We don't have to assume this. We'll generalize it in a bit, but it makes things a little bit simpler. And this section, I just kind of want to set up base intuition on graphs before we give the full generalization to simplicial complexes that'll have weighted graphs and stuff like that. So for now, let's assume we're deregular. So recall that the normalized adjacency matrix of a deregular graph corresponds to the following walk. That's very simple. It just maps the vertex V to a uniformly random neighbor. each with probability 1 over d, because we're assuming we're in a d-regular graph. So things are kind of simple and nice. And remember also, so it turns out this is indeed kind of one of the two walks that'll be very important for defining random walk expansion. But it turns out that when you want to generalize things to simplicial complexes, this maybe isn't quite the natural or quite the right way to do it. Instead, remember that there's actually another variant of this walk that you looked at on your homework, on homework 2 in the previous week, that we called kind of the lazy version of this walk. So recall as well, the lazy version of this walk. And you proved on the homework that this was, if we call the adjacency matrix A, this was A plus the identity over 2. And what did it do? Well, with probability 1/2, if you started at vertex V with probability 1/2, you stayed at V, right? So this was the lazy term. It doesn't move anywhere. With probability 1/2, it stays at the vertex that it started at. So with probability 1/2, V goes to V. And then with probability 1/2, if you condition not on staying at the same node, you spread uniformly around your neighbors. So here's the I over 2 is the lazy part. And then with probability 1/2, V maps to, again, a uniformly random neighbor. And that's the part that's given by A over 2. So this you showed on your homework. So it turns out that when we extend things to simplicial complexes, previously somehow this walk, the walk that was given by the adjacency matrix, is what we thought of as kind of the natural walk underlying the graph. But it turns out in kind of higher dimensions that the lazy walk will actually somehow be the natural walk. And instead of thinking about the lazy walk as a lazy version of the adjacency matrix, we'll think about the adjacency matrix as a non-lazy version of this other walk. And in just a second, I'll give I'll give the lazy walk an actual name. So I'm not just calling it the lazy version of the adjacency matrix, and we'll mostly be working with this. Even though kind of in the end, the adjacency matrix is what we will end up using, it's somehow going to be more natural, and we'll see this throughout the lecture, to kind of define things in terms of the lazy walks. Okay, so let me now give kind of another name or another way to view the lazy random walk. So I'm going to call this the node edge node walk. The node edge node walk. So on a graph, again, a d-regular graph G, I'm kind of just always assuming we're on some underlying d-regular graph G. The node edge node walk is given by the following two-step process. It's kind of a two-step walk given by the following two-step process. So basically, it just follows from what's given in the name. So the first step is going to be, we're going to move from nodes to edges. So given a node, again, I'm going to give you kind of the action of the walk on a node V. So given a node V, the first thing we'll do is we'll move to a uniformly random edge adjacent to V. So we'll move from a node to an edge, to a uniformly random adjacent edge. And let's call it VW. So this is just any edge that contains V, right? There are D of them because we're on a d-regular graph. So we move uniformly at random to one of the D edges surrounding the vertex V. So that's the node to edge step. And then there's the second step, which goes back from an edge to a node. So you're walking from node to node through an edge. So in the second step, VW gets mapped to a uniformly random vertex contained in the edge. In this case, either V or W with probability 1/2. Right, so maps to a uniformly random vertex contained in VW. So either V or W. In this case, there are no other options. We'll see there are more options when we move to the high dimensional case, but for now, there are only two options. And so maybe let me just write a quick claim. that the node edge node walk is in fact the lazy version of the adjacency matrix. Or the lazy version of the adjacency matrix gives kind of the transition operator for the node edge node walk. Okay, I'm not going to give a formal proof of this, but I'm going to show you intuitively why this is true. It should be relatively clear from definition. So let's take a look at a picture. That's probably the easiest way to see why this is true. So let's look at maybe just a single vertex V. Let's say we're on a 4 regular graph or something, and it looks like this. And let's say we start the node edge node walk at the center here. So what do? Well, in step 1, we'll look at all of the adjacent edges, right? So we'll look at every edge touching the blue node in the middle. I guess I should label this as V. And I'll pick one of them uniformly at random. So with probability 1/4, I pick one of these edges. Let's just say I pick this one. So now I've completed kind of the first step of the walk. I walked from a node to an edge. And now what do? Well, I'm going to move uniformly at random to one of the endpoints of the edge. So with probability 1/2, conditional on having picked this edge, with probability 1/2, I end up out here. And with probability 1/2, I end up at V. So I claim that kind of it should be immediately obvious that we get the 1/2 lazy part. Why? Because no matter what edge we picked in the first step, right? We could have picked this edge or this edge or this edge. There's always a 1/2 probability of picking the center again, right? Because you always pick an edge that contains V, and there's always a 1/2 probability of going to either side of the edge. So there's always exactly a 1/2 probability of staying at V. So there we get the lazy part. And then otherwise what happens, kind of conditioned on not staying in the middle, what happens is that we just pick a random edge and we go to the associated vertex that's not where we started. But this is exactly picking a random neighbor, right? This is exactly the same thing as picking a random neighbor. And what is the transition matrix of picking a random neighbor? It's the normalized adjacency matrix, right? So this is then exactly A plus I/2. It's exactly the same as the lazy random walk. So we'll see in a bit that this is also called, we'll see why in a bit, this is also called the upper walk or the up-down walk. And already it should be, relatively intuitive why this is the case, because you're starting at nodes, you're walking up to edges, and then you're walking back down to nodes. So people call this, in the high dimensional expansion literature, this is often called the upper walk or the up-down walk. And we'll generalize this to simplicial complexes a little bit later in the lecture. Okay, so I guess are there any questions kind of on review of the underlying walks of the graph, or the lazy version, or kind of this viewing it as this 2-step random walk from nodes to edges to nodes? So what we're going to do next is we're going to actually kind of formalize this 2-step process through what are called averaging operators, and we're going to have kind of an operator that moves things up and an operator that moves things down, and we're going to compose them, and that will give us this node edge node random walk, and it'll give us a nice way to have a general framework for talking about these walks. But before I go into that, any questions about kind of the definitions of these walks or background? Okay. If not, let's go ahead and actually get into kind of this formalization through what are called the averaging operators. These will be kind of our main tool to generalize things to simplicial complexes. And also just generally, they've been very useful in kind of the high dimensional expansion literature recently. So for now, we're just going to do them on graphs, but they will naturally generalize to simplicial complexes. So let's go ahead and look at the definition. The averaging operators. So I think Shahar defined these spaces before, but let me just kind of recall. So we're gonna define these as kind of formal operators on the space of functions on vertices and edges. So as a reminder, C1 or kind of C1x, C1g, or C1x, we'll just call it C1, will be the space of functions from vertices to the reals. So this is really just like assignments of real numbers to the vertices. And we'll let C2 be the space of functions from edges to the reals. So these are both vector spaces, right? We can define formal linear operators on these vector spaces. And so what we'll do is we'll define two averaging operators. We'll define the up operator, which is going to map functions on vertices to functions on edges. And we'll define the down operator, which will lower functions on edges to functions on vertices. And I'll say in just a second why I'm calling them averaging operators. So what does U1 do? Well, given a function f, so U1 on f, so f is in C1, right? U1 maps C1 to C2. So f is a function on vertices, and then U1 of f takes in an edge. So what's the value of U1f on the edge VW? Well, I'm claiming this as an averaging operator. And what do I mean? Well, if I have a function on vertices and I give you an edge that consists of two vertices, what's the natural thing to do? I'm just going to take its average value over the two vertices, right? So this is equal to 1/2 f of v. So f on 1/2 f on one end of the edge, and 1/2 of f on the other end of the edge, right? F of w. So this is kind of the most natural averaging procedure that you could come up with. And so we're kind of raising the function in function space. We're raising the function from a function on vertices to a function on edges by averaging downwards, right? We're actually, even though we're lifting the function up, we're averaging downwards. And similarly for the down operator, we're going to kind of do the flip of this. So let's see, what's d2 of f? So f is now a function in C2. d2 of f is a function on vertices, right? So it takes in a vertex v. And now we're going to do the same thing where we just average up. Now we're going to look at the average value on every edge that contains v. Right, so what is this going to be? Well, for simplicity for the moment, I'm assuming our graphs are deregular. Right, so we're going to have a 1 over d normalization factor up front. And then we're just going to look across all of the nodes adjacent to v, or all of the edges that are containing v, and we'll sum over the value on that edge. Right, so maybe again it's easy to see through a picture. Let's say we have a function on edges, so maybe it takes value 2 here, 1, 0, and 5. So I say I want to ask, let's call this v. I want to ask what's the value of the down operator. So call this function f on edges. What's the value of the down operator on the middle here on v? So what's d2 f of v? Well, there are 4 edges, so it's 1 over 4. And then I just sum over, all the edges that contain v, which is 5 plus 2 plus 1, which is conveniently 8. So the value here is 2. All I've done is I've looked at everything touching v, and I've averaged over it. It's a elementary averaging operator. But hopefully you're kind of already starting to see the connection with the node edge node random walk, right? In the node edge node random walk, we started at a vertex. We picked a uniformly random edge. Then we went from an edge to a uniformly random vertex. That's exactly what these operators are doing. And so we're going to be able to use them to define as a way to define the node edge node random walk. But before I do that, maybe let me give a little bit more information about these averaging operators. I think in particular, it's maybe instructive to view them as matrices, to see what do they look like as matrices, right? I've defined them so far as formal linear operators, which is great in theory, but in practice, it's maybe helpful to understand if I assign kind of the standard basis to C1 and C2, what do these actually look like? So this will be instructive. So I guess let me first do a quick kind of reminder definition. So we're going to let, so again,
Max, there's a question here in the chat.
Oh, thank you. I missed that. What does the value under sigma say? That says W sim V this is W adjacent, maybe W in the neighborhood of V. I'm just summing over edges that contain V. I think that's what the question was. Okay, great. Yeah, sorry. I'm just summing over all the edges that contain V. Okay, thanks, Shahar, for pointing that out. Okay, so I'm just going to define a matrix quickly that'll help us with figuring out what these operators are. So let R denote the node edge adjacency matrix of our underlying graph G. And what is this? Well, this is kind of the V by E matrix indexed by vertices and edges. That's just like the incidence matrix, right? So RVE, where V is a vertex and E is an edge. Well, this is equal to what? Well, it's equal to 1 if V lies in E, and 0 otherwise, right? So this is just the matrix that's 1 when a vertex is included in the edge, and 0 otherwise. You can view this as the bipartite matrix between kind of the level of vertices and edges if you want to. But this is a simple object. It's just the incidence matrix of vertices with edges. It's just another way of recording the graph. And I claim that R basically gives the averaging operators. So what do I mean by that? Well, first I have to pick a basis, right? So if I want to talk about matrices, if I want to move from kind of formal linear operators to matrices, I have to pick a basis. So I'll just pick the standard basis. We'll associate C1 with R to the V and C2 with R to the E. Then I claim the following is true. I claim that U1F is equal to 1/2 R transpose F, and that D2F is equal to 1 over D RF. So basically, I claim that these formal averaging operators that I've defined are really just the node edge incidence matrix and its transpose. I'll give maybe a quick intuitive explanation of why this is true. I'll leave maybe the full proof as an exercise. I think it's worth working through these things to make sure you understand what's going on with the up and down operators. But let's just look at maybe U1 of F. So why is this equal to 1/2 R transpose F? Well, first of all, let's draw out our transpose, and hopefully this will maybe help understand this matrix as well. So R transpose is kind of E by V, right? The rows are indexed by edges, the columns are indexed by vertices. And what does this look like? Well, if you have an edge VW here, you have maybe V indexed here and W indexed here, then this is 0 everywhere except V and W where it's 1. So if you multiply this by F, now in vector form, what are you going to get in the kind of VW spot? Well, we look at just the inner product of that row with F, and this is exactly F of V plus F of W, right? So if we hit this with 1/2 out front, like we're doing here, you get 1/2 V plus 1/2 W. And that's exactly how we defined the op operator, right? So this is basically just straight from definition from this matrix. I'll leave the other direction to you. So maybe I'll pause again, because these are, at least the up and down operators are pretty important definitions. Are there questions about kind of these averaging operators, the up and down operators, before we move on to using them to define kind of the random walks? So these are the operators that basically will generalize to simplicial complexes to define our higher dimensional version of expansion. Okay, if not, then let me go ahead and make another claim. If we compose these operators, so if we compose D and U, which remember is U is lifting functions from vertices to edges kind of by uniformly random averaging. The down operator is lowering functions from edges to vertices uniformly at random. It shouldn't be too surprising that this is exactly the node edge node walk. And I guess I'll say here, this is what is commonly called the upper or up down walk. And now, maybe it was clear before because we were kind of moving from vertices to edges to vertices, but now it should be very clear, right? Because we have these two operators. One of them is lifting functions, one of them is lowering functions. And so kind of in the high dimensional expansion literature, you'll usually see this referred to as either the upper or up down walk. I think the node edge node or vertex edge vertex is more from the graph side of things. You'll usually see it as upper or up down when you look at the high dimensional expansion literature. So the proof.
Yes. Can I just one comment just so there's no confusion? So when you write like this D2U1, so you always read it from right to left. So you're always acting on the right. So you first apply U1 and then you apply D2. So up one moves you from nodes to edges, and then D2 moves you from edges to nodes. So
no, that's not correct. That's correct on functions, but it's not correct on the walk.
Functions.
Yeah, I'm gonna clarify this in just a second.
Okay, fair enough.
Yeah, so there is something subtle here that Shahar is talking about that is a little bit confusing. And we can spend a little bit on it because it's an important fact, and different versions of the literature kind of deal with it differently, and it's a little annoying. So I am still going to leave the proof as an exercise.
Oh, that's right. The random walk the other way around.
Yeah, so it's the other way around. So it turns out that even though the down operator, lowers functions and the up operator raises functions, remember that I kind of highlighted that they do this by averaging in the opposite direction, right? So the up operator lifts a function from vertices to edges by averaging down, and the down operator lowers functions from edges to vertices by averaging up. And it's these averaging processes that are actually giving you what's going on in the random walk. So when you move up in the random walk, it's actually corresponding to the action of the down operator. And when you move down in the random walk, it's actually corresponding to the action of the up operator. So it is read left to right. The down operator is actually corresponding to the up step, and the up operator is corresponding to the down step, which is unfortunate. But kind of there are two natural ways to define these operators. You either think about them as operators on function spaces, in which case the definitions that I have given here make sense, right? So if you think about the up operator and its action on a function, it does indeed lift a function from level 1 to level 2. And so it makes sense to call it the up operator. And similarly, the down operator lowers functions from level 2 to level 1. And so it makes sense to call it the down operator. But if all you care about is the random walk and not actually how these things act on functions, then it would make sense to define it the other way, right? Then it would say, well, the up operator is actually the down step in this walk, so we'll call it the down operator. And the down operator is the up step in the random walk, and so we'll call it the up operator. And unfortunately, if you look at the sampling literature, this is how they define it. But if you look at the HDX literature, they define it the way that we have. So you have to be very careful when you look at kind of different sets of literature for the down and up operators, because they're defined in exactly the flip manner in these two different sets of literature. So if you're looking at kind of a structural HDX paper, it'll be defined usually in the way that we have defined it. If you look at kind of a mixing sampling problem paper that uses high dimensional expanders, they usually will define it the opposite way that we do. So I learned this by being very confused about a sampling paper for several hours. So, take this as a warning. If you try to go read kind of application papers, be very careful about how they're defining these operators. They'll be the same things, but possibly flipped. Okay, so that ends my PSA about this. Shahar, do you have other?
Yeah, but then we also saw something very similar in last lecture. So the way we define the adjacency matrix, right? So we said that we defined it in a transposed way, so the way it acts is an average in a function. So its action on the left was the action as a random walk, moving probabilities to probabilities. And its action on the right was as an averaging operator, moving functions to functions. So it really depends. You have the same operator, and the only question is, do you operate on the right or operate on the left?
Right. So just like the adjacency.
It's the same, but yeah.
Just like the weighted adjacency matrix, yeah. And we're going to get to this again in a little bit. if you operate on the right here, D2U1 is looking like an averaging acts as the averaging operator. If you multiply by a vector on the left, it'll act as the random walk. It'll give the kind of transition probabilities of the random walk.
Of course, when the graph is deregular, they're the same. It doesn't matter.
Yeah.
But it,
So in this case,
it does matter when you're in a non-regular walk or in a weighted graph, and then they're not the
same. Yeah. So in one sense, it's kind of obvious that this is the node edge node random walk, because all you're doing is uniformly averaging over neighboring edges and then neighboring nodes. But there's a little bit of subtlety because of kind of the directions things are going are a little flipped, which can be a little hard to wrap your mind around. It's worth spending some time thinking about this after lecture. Okay, so maybe I'll pause and ask if there are any questions about that discussion. So I think it can be a little bit confusing before we move on. We're almost to the point that we can define random walk expansion.
Can you explain again, like the difference between left operation and right operation?
Yeah, so this is just like if you remember back when we had like the weighted, say this is like a weighted adjacency matrix of a graph. We defined this so that it was actually kind of the transpose of the transition matrix of the walk. So if you want to say, look at the, where does this walk send the vertex t, you would multiply by 1t transpose on the left. So basically, if you want to kind of like do the walk, you would apply the function that you want to take the walk on, the distribution on the left side of the operator. And if you instead did looked at f on the right side of the operator, this gives you the expectation of f over neighbors, over kind of neighbors of each vertex. Right. So on the right, it acts by averaging. It looks at the average of v over neighbors. And on the left, it's actually the underlying random walk, if you like apply the transition probabilities. So left, you'd apply like pi, and this would map it to as the random walk does. On the right, you apply a function, and it averages the function over neighbors. I mean, they're both the same thing. They're just transposes of each other. Yeah, I don't know, Shahar, if you have a better way to explain this.
Okay.
Honestly, the best way is just write the calculations and see that it works. And I mean, I don't know if there's any better intuition. There's just somehow dual operators, but this gives no intuition. I mean, to me, the intuition is from you write the equations, very simple equations, and somehow you convince yourself it works. Yeah.
Okay. Yeah, I wish I had a more intuitive answer for you, but yeah, that's pretty much my understanding of it too. Is that on one side, if you write it out, kind of it's obviously averaging. On the other side, it gives you the transition probabilities. If you write it out, you should be able to see this. Yeah, but a good question. Okay, so let's move on to the next walk I want to talk about. So we actually need kind of two walks to define this version of expansion. One of them is going to be the upper walk, or really the non-lazy upper walk, which is just the adjacency matrix, but forget that for now. We now think of the upper walk as kind of our standard walk rather than the adjacency matrix. And the second is going to be kind of a converse walk. So instead of taking a step up and a step down, that's called the upper walk. We're going to define a walk that takes a step down and then a step up, and that's called the lower walk. So definition. Lower walk. And maybe let me give some intuition for this first. In particular, on a graph, it's pretty clear what it means to walk from a node to an edge to a node, to take a walk kind of up from vertices. It's maybe not so clear what it means to take a walk down, because usually when we think about graphs, there's nothing below vertices. Vertices are kind of the base level. But remember that in a simplicial complex, there actually is something below vertices. There's the empty set. So kind of looking ahead, and we will be thinking about these as simplicial complexes. So this does make sense to define. What will the lower walk be? Well, we'll kind of walk, if I draw out a graph here. If I draw out some graph, what does it mean to take the lower walk? Well, I'm going to walk from a vertex down to kind of this invisible level 0. That's actually the empty set. So I'll start at a vertex and I'll walk down to the empty set. And then every vertex, then I'm going to walk uniformly at random up to vertices. But every vertex contains the empty set. So what does this mean? I'm just going to spread uniformly out among vertices. This is a little weird at the moment. It'll make a bit more sense when we view things as complexes. But at the moment, think of there's kind of this invisible level 0, that's the empty set. And you walk from a vertex down to the empty set. And there's only one option. There's only the empty set. So everything just walks down to the empty set. And then it uniformly will average up over things that contain the empty set, which is all vertices. So all this walk is doing is it will map any vertex to a uniformly random vertex. So for simplicity, I'm just going to define the lower walk by its transition matrix on a graph. The lower walk I'm going to define to be 1 over n times the all ones matrix. So it's on an n vertex graph. So it takes any vertex and it just maps it to a uniformly random vertex. Doesn't matter where you start. You always just go to the uniform distribution over vertices. And somehow intuitively to you, I'm claiming that this corresponds to this process where you walk from a vertex to the empty set to level 0 and then back up uniformly at random across the set of vertices. And kind of why am I making a big deal of defining it in this intuitive way? Well, it's how it matches up to the averaging operators. And so in fact, we can also write the lower walk in terms of averaging operators. But instead of defining the averaging operators at level 2 and 1, we'll define the averaging operators at level 1 and 0. So let's just do this. So this will be our second version of the averaging operators. So we already have C1 and C2. We're also going to need C0 here. And so this is basically just constants. But what is it actually? This is the space of functions from the empty set to the reals, which we usually just associate with the reals. Okay, so this is kind of the space of functions on level 0, where level 0 is the empty set. Okay, so what are our operators now? Well, we'll have U0 that maps C0 to C1, and we'll have D1 that maps C1 to C0. So these will just be the analogs of what we defined before, but one level down. So what is the op operator on level 0? Well, it takes in a function on the empty set, which is just a constant. And then, so where does this map a vertex? Well, we're just going to average down like we did before, but there's only one thing to average over, right? There's just the empty set. So what's the natural thing to define here? This is just, f of the empty set. It's just whatever the constant is that's given by f. This is kind of the only choice. Like there's only one value to average over it. You just average over one thing. There's kind of nothing else you can do. So what about D1? This is slightly more interesting. So this takes in a function over vertices. And then the only value we have to look at is the empty set, right? Because this is now a function on C0. So it's just going to be a constant. So again, we're going to get the value now by averaging up, right? The down operator lowers functions by averaging upwards. So what is this? Well, again, kind of the only natural choice is that you average over everything because everything contains the empty set. So this is just the global expectation of f over vertices. So these are kind of, almost like a trivial version of the walks. One of them is an average over one thing. One of them is an average over everything. When we raise things to higher levels in the complex, these operators will be a little bit more, the kind of down version of the walk will be a little bit more interesting than just the kind of walk that maps things uniformly at random. But for now, it's okay. This is actually what we want. So I guess let me just quickly make the analogous claim. That's, what do I want to say? That U0 D1 is the lower walk. So this is, in particular, 1 over n times j. So I'll leave the proof again as an exercise. But it should be fairly intuitive. We are kind of just doing this process where we walk down to, the empty set, which contains everything, and then we're averaging uniformly at random. So it should be somewhat intuitive that the walk that kind of maps V to the uniform distribution is given by this process. Okay, so maybe let me just use these to define a random walk expansion, and then we'll pause for questions. So we finally are now able to actually define, I mean, okay, admittedly, I probably could have done it without all of this machinery, but we're now able to define random walk expansion in a kind of a natural way that will extend to simplicial complexes, which was, kind of the main goal of this. So let's go ahead and do this. So we call G a random, or I guess I should say a gamma random walk expander. If kind of morally the following is true, the non-lazy upper walk, which remember is just kind of my new name for the adjacency matrix, is spectrally similar to the lower walk. So what do I mean by this formally? Well, the non-lazy upper walk, which is the adjacency matrix, minus the lower walk, which is 1 over nj. I'll write these in a second in operator terms, but for now, let's just look at it like this, is less than gamma. And let me just kind of morally argue that this is a reasonable definition, just kind of what we know about mixing of the associated random walk versus the two-sided spectral expansion, right? We kind of know that if A is a spectral expander, it should mix quickly to the uniform distribution, right? And what is 1 over nj? Well, it's just like all of the rows are the uniform distribution, right? This is just the matrix that kind of immediately maps everything to the uniform distribution. So A, we know kind of if it's a good spectral expander, it kind of very quickly converges to the uniform distribution. And we're saying, well, if this is kind of spectrally similar to the matrix that immediately takes everything to the uniform distribution, then it should be a kind of a good two-sided spectral expander. This is the intuition. In fact, we'll see in a second they're exactly the same, but kind of morally, this is why you should already expect them to be the same, even if you haven't thought about it much. Okay, so how do I rewrite this in terms of the operators? Let me just do this quickly, I guess. Well, we know that 1 over nj is equal to the lower walk, right? So this is equal to u0 d1. And we showed earlier that d2 u1, or at least I claimed it, I guess, is equal to the kind of lazy version of the adjacency matrix. So in other words, we can write A is equal to 2 d2 u1 minus the identity. So an equivalent statement in terms of the averaging operators is what? 2 times the upper walk minus kind of its lazy part, minus the identity, minus the lower walk, or rather the kind of this term is spectrally similar to this term. I guess I should note what is this norm? This is the spectral norm. As a reminder, that's just the top eigenvalue and absolute value of this operator. And both of these are self-adjoint. So this has a eigenvalue decomposition, etc. So this is perfectly well defined. So we're just asking kind of more formally, we're asking what is the top eigenvalue of the non-lazy upper walk minus the lower walk? And let me just say quickly, why is this, I said morally, why is this reasonable from kind of what we know about mixing? Why is this actually just exactly the same? So I claim that G is a gamma random walk expander if and only if G is a gamma two-sided gamma spectral expander. So I claim that this is actually just a different way to view exactly the same definition that we're used to on graphs of two-sided spectral expansion. And again, I'm gonna cheat and leave the proof as an exercise, but I'll at least give essentially why this is true. Basically, you can think of 1 over nj. So A has, what's the definition of two-sided spectral expansion? A has a trivial eigenvalue 1, and then it has kind of the second through nth eigenvalues, and we're bounding the size of those eigenvalues. So when we subtract off the lower walk, when we subtract off 1 over nj, what we're doing is we're basically just subtracting off the trivial eigenvalue. So we're basically taking the trivial eigenvalue from 1 to 0. And so what we have left is all the remaining eigenvalues. We have lambda 2 through lambda n left. And what is the spectral norm of that matrix of lambda 2 through lambda n? Well, it's literally just the largest of lambda 2 through lambda n in absolute value. And that is the definition of two-sided spectral expansion. Right, so this follows from the fact that kind of 1 over nj essentially subtracts off the trivial eigenvalue. And this isn't really too hard to prove. Maybe it's worth going through after class, but it shouldn't be too hard to see that this is the case. Okay, so that basically concludes what I wanted to talk about on graphs before we extend it to simplicial complexes. So I'll pause for questions. Are there questions on this random walk definition, on why it's exactly equivalent to two-sided spectral expansion, or on the operators? Anything we've covered so far before we start generalizing this stuff to higher order random walks? Okay, well, if not, what I actually want to do, and so we maybe won't quite have time to cover everything I want today, but that's okay. What I want to do is actually give an informal introduction to higher order random walks and the averaging operators on simplicial complexes before we start really working on the formality. And to do this, I've cheated slightly, and hopefully this will work. I have some slides prepared that we can look at, so that I don't have to redraw a simplicial complex 17 times, because that would be really unfortunate. So let me see if I can get this mirroring thing to work. So is it gonna? Okay, it looks like it's gonna work. Great. Okay, so I have some slides here, and what I want to do is I want to take a look at the node edge node random walk from two different perspectives. We're going to look at it kind of as its standard version on a graph, and we're going to look at it on this weird object I have written over on the left, which I claim is like a nice way to view simplicial complexes, called the Hasse diagram. So let me maybe take a moment to explain, what the heck's going on over here on the left, because it's actually a very natural and a very useful way to represent simplicial complexes. So basically all I've done over here is I've stacked up the levels of the complex, right? So I start with x0, that's the empty set. I go to x1, which is vertices, x2 is edges. And then if I had a higher dimensional complex, here I don't, here it's just a graph. But if I had at higher levels, I could just keep stacking them, right? I would put x3 here, x4, x5, x6, etc. I just stack all these up. Then I kind of write out all of the values here. And then I write edges between the levels by inclusion, right? So the empty set, well, that's included in everything. So I draw an edge from the empty set to all vertices. And then I look at maybe 4. What's 4 included in? Well, 4 lies in 3, 4, it lies in 2, 4, and it lies in 1, 4. So I put in these edges. So if you're familiar with maybe enumerative combinatorics or something, you'll recognize this as like the inclusion poset of the object. But there's nothing complicated going on here. All I'm doing is stacking up the levels of the simplicial complex, writing them out as sets on each level, and then drawing edges when one set is included in the other set. That's all that's going on. Simplicial complexes kind of geometrically get a little difficult to visualize after 3 or 4 dimensions, at least for me. Maybe there are people who can do that, but I can't. But this poset view, right, is just stacking, somehow we've simplified things to 2 dimensions. It's just some stacked view in 2 dimensions where we can actually kind of understand what's going on in the high dimensional simplicial complex structure. So, even beyond kind of analysis of higher order random walks, I claim this is a really useful way to write out or view simplicial complexes. So any questions on kind of the definition of this complex view? It's called a Hasse diagram. It's very useful. It would make sure people understand what's going on. Pause for a second. Okay, great. If not, let's take a look at the node edge node random walk from kind of 2 viewpoints: the normal viewpoint you'd see on a graph and the complex view. And hopefully kind of by looking at this on the complex view, it's going to become very obvious how we're going to generalize these things to simplicial complexes, right? Before I was just kind of telling you about these general operators, and maybe you could kind of somewhat formally guess what these are going to look like on simplicial complexes. And I'm going to claim that as soon as we draw things out like this, it's really going to become quite natural. So, okay, let me actually, show that this is true. So let's take a look at the node edge node walk on the graph versus the complex. So we start at some vertex, maybe 1, and let's look at the action of the walk on this vertex. So what do we do? Well, the first thing we do in the node edge node walk is we look at all of the adjacent edges to that node and then we'll pick one uniformly at random. So over here on the graph view, we're just looking at all the edges that touch 1 in the graph, right? And we're gonna choose one of these uniformly at random. And over on the simplicial complex view, we already start to see, I mean, they're of course the same, but we already start to see kind of a different viewpoint of things. Whereas instead of kind of things touching 1, we're gonna look up a level in the complex, right? We're starting at x1, and now we're gonna look up in level x2, kind of by inclusion, and pick something randomly that 1 is included in. So I've highlighted them here. And so we'll pick one of these uniformly at random. Let's say I picked 1, 4. I claim that was a random choice. So now we apply the same step. We've completed the node to edge version of the walk. Now we'll walk from an edge to a uniformly random node contained in that edge. So down on the graph view, what does this look like? Well, I've just highlighted the vertices that touch the edge, right? That's all I've done. But over on the left, we again get kind of a more of this down-up view of things, where I started on level x2, and now I'm looking down at level x1 at the things that are, the sets in x1, the vertices that are contained in 1, 4, are 1 and 4 on the level down. And then I'll pick one of these uniformly at random. Maybe I pick 4. If I'd picked 1, that would have been fine. That would have been the lazy component of the walk, right? But let's say I picked 4. So we've completed one step of the vertex edge vertex random walk, right? So over on the right, it basically just looks like we've moved from 1 to an adjacent node, so 1 to 4. But over on the left, we kind of get a different view of things that much more closely matches our intuition of kind of the up, down, or upper walk, right? Because what did we do on this diagram? Well, we started at level 1 of the diagram. We walked up uniformly at random to level 2 of the diagram, and then we walked back down to level 1, so that we had a walk kind of on level 1 from 1 to 4, but we did it through level 2 of the diagram. So we took a step up and we took a step down. So this is the up, down, or upper walk. So this is kind of why this intuition makes a lot more sense on the complex view of things when you're viewing things as kind of this Hasse diagram. And the key here, and the reason I claim this extends naturally to complexes is, well, let's take a look at what happens when I maybe add triangles, right? So before I was really just looking at a graph, I kind of cut things off at level 2, but I can add in, all the possible triangles. So in this case, 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. And this is called the complete this is the complete complex on 4 vertices in 3 dimensions. And the point here is that this up-down, this up-down process, there's nothing forcing me to start at level 1, right? Walking up a step in this diagram and down a step in this diagram, that could happen at any level, right? So in particular, I could start at an edge, say 1, 4, then I could walk to a triangle, 1, 3, 4, that contains 1, 4, uniformly at random, and then I could walk back down to an edge, and that would be the edge triangle edge walk, right? I could, if there were x4, I could start at a triangle, and I could walk to a pyramid, and then I could walk to a triangle. That would be a triangle or triangle, pyramid, triangle walk. Or I could walk from a triangle to an edge to a triangle, right? On this diagram, walking up and down is a perfectly natural operation. I'm just kind of uniformly at random moving up and down. And it turns out, we'll see these movements are given by the up and down operators. But the point is that this is some very natural, as soon as you look at the lazy versions, these upper and lower walks, there's some very natural way to extend these to complexes, where all you do is you fix a different level. You look at the upper walk on the ith level, and it just starts at level I. It walks up a step to level I plus 1, and then down a step to level I. And it's kind of a natural analog of the node edge node random walk. So maybe any questions about this kind of informal introduction to the upper walks on simplicial complexes? Okay, so if not, I also kind of want to give an informal view of the down and up operators before we move into formally defining them. And then we'll actually go formalize all of this stuff. But hopefully you'll kind of have the base intuition for what's kind of actually going on behind the scenes, that it won't just look like a bunch of, math and operators, and you'll actually be able to think about, well, this is, just on the ith level of a complex, and we're walking a step up and we're walking a step down. There's a very natural kind of pictorial way to view these things. Yeah.
So just to be clear, so you're always going to be keeping, like, you're not going to be going down, like if you start at 2 and go up to 3 and back down to 2, you're never going to go like down below 2, right? Or like does the can you ever have like two down in a row? Okay.
Yeah, absolutely. So we actually, I'm not sure we will talk about this in this course, but so there are these upper and lower walks are just examples of what are called higher order random walks. And just as you suggest, there are other versions of these that are actually very important in application. So
I
for
see.
instance, you could start at a vertex 1, and I could, instead of walking up 1 and down 1, I could walk up 2, right? I could walk up to an edge and then up to a triangle and then down to an edge and then down to a vertex. So this would be up, up, down, down. And this is
Right.
also a perfectly valid higher order random walk.
Mhm.
And you could kind of do these crazy things like maybe you were suggesting. So in the upper walk, the walks that I was talking about, the upper and lower walk, you'll always go up one step or down one step. But there are, you can define all these other walks. So I could walk up 1 and then I could walk down 2 and then I could walk up 1. And that's a perfectly valid walk as well. And all of these, in fact, are just different combinations of the averaging operators. So these are actually called pure walks. We won't kind of go into the literature in which these are used. But yeah, these turn out to be a very useful set of walks as well, where you kind of can walk multiple levels up and down the complex. It can kind of look like whatever you want it to look like. Good question.
I see. Thank you. So wait, sorry if I might ask a follow-up.
Yeah, of course.
So like so generalizing these like higher order random walks, like would it be you always need to define like a specific ordering, or could it be like you flip a coin to decide whether you're going up or down on this next step, or
I have not thought about that. That's an interesting question. I mean, you could define that.
right.
Shahar, would that end up being the same for some reason, or is that a different object? I guess it's a different object, right?
Listen, I mean, yeah. So for various reasons, you want to look at walks that start and end at the same level.
Right.
So for example, you can say something like, with probability 50%, you go up and down, and then with probability 50%, you go down and up. That's still okay because it's a mixture of two walks that start and end at the same level. What you were suggesting is, well, let's say 50% go up and then to go down, but this actually mapping to different spaces. If you think of them as, random walks, you could say, well, maybe it's okay because they map me into like, one is like a distribution of the nodes, one is a distribution of triangles, and that's already a bit weird. But if you think of them as operators on function, then it's even weirder because they just map into different spaces. They're not even, so they're not really well defined in that sense.
So okay, I should note that. I should note, Shahar, that these actually are used. The walks that go between different levels are still important in various applications. We won't cover any of them in this course, but.
So you mean beyond a mixture of pure walks that start and end at the same level?
Yeah, for sure. When we do hypercontractivity, we care about the walk that goes up 1 step and then down 3 steps. Right? We often care about walks that go to different levels. Usually they're not random. One thing to note about this random version, Pawn, is that I think with some probability, like if you're at level I with probability 2 to the negative I, you'll hit the empty set, and then it'll just become uniform, right?
Right. Yeah.
So at some point it'll just, all those walks will always become uniform, I think, which makes them maybe not so interesting. But again, I haven't thought deeply about this, so I'm not totally sure. But
next, do you have an example of walks that sort of where you don't know what the level is going to be?
No. Always some fixed levels. I don't know how it would be if you don't know what the level is going to be.
Yeah, but again, you can define whatever you want. The question is this useful for anything?
Yeah, is it useful?
Yeah,
it might be,
Yeah. Right.
Yeah, I mean, it reminds me of kind of the, looking at probabilities that, given this half up, half down step, that you'll end up at a certain spot. I just don't know if it's, how useful it would be for something. Yeah, interesting question. Yeah. Okay, so let's move on to the informal definition of the averaging operators. Trying to think of, I think we'll be able to get through maybe proving their adjoint. Okay. So Okay, unsurprisingly, we've kind of already hinted at this. The way that we formally will define these up-down processes are again through the up and down operators, through averaging operators, just generalized to every level of the complex. So basically, as a reminder, kind of CK will denote the space of functions on K faces, so functions from a K face to a real number. And we'll have two type of operators, like we did before. We'll have the up operator and the down operator. So the up operator on level K lifts functions from K faces to functions on K plus 1 faces, again by averaging down. So let's take a brief look at an example. Let's say f is a function on edges, and let's say it takes value 1 on these bolded edges and 0 elsewhere. Let's look at the raised value, u2 of f. What is u2 of f on a triangle? Well, we just average down in the complex, right? So we look down at, everything, every edge that's contained in 1, 2, 4. We look at 1, 2, 1, 4, and 2, 4, and we average over their values, which gets us 2/3, right? So the average of u2f on 1, 2, 4 was 2/3. And this is just the exact analog of this averaging process we were doing on graphs, right? Except now we have a triangle. The down operator is similar. It lowers a K face it lowers a function on K faces to a function on K minus 1 faces. D2 we actually already saw, but it'll be the same on a simplicial complex. If we have the same function f and we want to look at D2f of say 2, we average up in the diagram. So I just want to go through, even though this is the same, I just want to give it from the diagram viewpoint because I think it gives a nice kind of way to think about the operators. So now we average up in the complex, and we see that, so 2 is contained in 1, 2, and 2, 3, and 2, 4. And this is, 1, 0, 0, and we average and we get 1/3. So this is assuming things are uniform for now, and we'll branch out to actually kind of using the distribution that comes with the complex. But for now, just intuitively, this is what's going on kind of for a basic uniform example. Okay, so that's the end of kind of the informal version of these walks that I wanted to give. So unless maybe there are any more questions, let's try to at least kind of give the actual definitions of the averaging operators and maybe prove one thing about them if we have the time. Feel free to stop me if you have more questions about kind of the intuition here. Otherwise, we will formally define the averaging operators now. On a complex, we already defined them on a graph, but now we'll define them for weighted complexes. And before I actually give you the definition, there's one kind of subtle point that I want to make about the distribution associated to a weighted complex. So in particular, recall that on x pi, so let's say x pi is a weighted simplicial complex. In the past, and maybe pi I'll write as pi is equal to pi 0 through pi d. And remember, the way that we got these distributions is we picked pi d to be arbitrary, and then we kind of induced pi I by choosing something from pi d and then picking a uniformly random I subface. And this gave us this series of distributions from pi d down to pi 0, one across each level of the complex. And in the past, we've kind of only thought about each pi I individually. But in fact, I want you to recall that pi is actually a joint distribution. There's not necessarily any reason to only think about the marginals. Pi is a joint distribution over chains of faces, one in each level. So over kind of sigma 0 lies in through sigma d, that lies in kind of the union, like a chain of things, one face from each level of the complex. So in the past, we were kind of just focusing in on like sigma 3 or sigma 2 or something like that. And we were looking at the distribution coming from the marginal, coming from pi 2 or pi 3. But it turns out that it'll be useful for us now to actually work with the full joint distribution over a chain of phases rather than the marginal. So just as a very basic example, let's look at what this looks like on an expectation just on a function on level k. So let's say f is in ck. And we want to look at the expectation over the joint distribution. So over sigma 0 through sigma d, drawn from capital pi. So whenever we draw from capital pi, we're drawing a full sequence of d plus 1 faces. And let's say we just want to look at the value of f. Well, f is a function on sigma on level k, right? So we're going to draw the whole chain of faces from the joint distribution, but we're just going to look at the average value over the k face. So, it's not too hard to imagine. This is just the same as the expectation over the kth marginal, right? So this is the same as the expectation over pi k of, say, f of tau. But my point is that we can look at this from either direction, right? We can look at it just as the marginal distribution pi k, like we've been doing in the past week and a half or so, or we can look at it in terms of this joint distribution. So why would we want to look at it in terms of this joint distribution if so far all I've shown you they're exactly the same? Well, it turns out that kind of it maybe already would have been useful to do this, and we didn't talk about it before because we wanted to kind of give things in terms of the marginals and show you both ways of doing this. But it's useful for when you want to talk about moving kind of between levels of the complex. So here we focus just on level k. But remember that when we proved like Garland's method last week, what Shahar did is he kind of used the connection between, I guess in that case, vertices and edges, or edges and triangles, right? The proof went something like, okay, we have this distribution over edges that we want to analyze, and how are we going to analyze this? Well, we're actually going to say, well, how do we sample an edge? We can sample an edge by sampling a triangle. We can sample something from pi 3, and then we can sample an edge conditional on that triangle. So essentially what you're doing is you're sampling something from pi 3, and then conditionally sampling something from level 2, given level 3. And instead of doing this kind of conditional, jumping through hoops, well, drawing something from a marginal and then something conditional on that marginal is just the same as drawing it from the joint distribution. So instead of kind of doing all of this conditional work, we could just always work over the joint distribution and we wouldn't have to do this. And hopefully you're going to see in a minute what I mean by this if we have time. I think we should. So why use the joint distribution? Why? It's kind of useful for working with conditional probabilities between levels. So useful for conditional probabilities between levels. And this is, a bit vague at the moment, but we will very explicitly see this used in the upcoming proofs. So it should become clear what I mean. Okay, so with that out of the way, let me go ahead and define the averaging operators. So definition, averaging ops. Okay, so we've already kind of talked about what the space of functions, ck, etc. are, so I'm not going to redefine these. But let's look UK. So this is a function that maps ck to ck plus 1, operator ck to ck plus 1. And it's given, so we're going to give it in terms of this joint distribution instead of looking at the marginals, because it'll be a lot simpler to express. Right? In particular, UK of f, so this is f is a function in ck, applied to a k plus 1 face. This is just going to be the expectation over the joint distribution, sigma 0 through sigma d, drawn from the joint distribution, of f of sigma k, given that sigma k plus 1 is equal to tau. So back in the diagram view, what are we doing here? Right, we have level xk, and we have level xk plus 1. So what are we doing? Well, we're fixing some tau on level k plus 1, and then we're just looking kind of uniformly down at random. We're going to average across things that are contained in tau. So in the diagram view, this still just kind of looks like this uniform down averaging, but we can also write it in terms of kind of this joint distribution. We draw a k plus 1 face, tau, and we condition on that k plus 1 face, and we look at the average value conditioned on tau. Okay, so maybe it's a little bit easier to write this kind of the explicit version. Maybe it's a bit easier to understand it looking at both directions. So what does this look like? Well, we fix a k plus 1 face tau, then we look uniformly at random at all kind of sub k faces. How many sub k faces of a k plus 1 face are there? 1 over k plus 1. So we get an averaging factor, a normalization factor out front of 1 over k plus 1. And then what are we doing? Well, remember the way that we defined kind of pi k, given pi k plus 1, was, if you have tau, you just pick a uniformly random k face. So we'll now sum over all of the k faces contained in tau of f of sigma. right? So this is really just this averaging procedure again, but at times it'll be very useful to view it through this joint way of thinking of things. At times it'll be useful to use the explicit version. You know, so they're both useful in different circumstances, so it's worth kind of knowing both ways. So let's similarly define the down operator. So the down operator dk plus 1 lowers functions from ck plus 1 to ck. So we have dk plus 1 f of tau again. So now tau is a k face, not a k plus 1 face. And again, one of the nice things about using this joint version is that you can really see the similarity between the up operator and the down operator. If you write out, you know, the explicit versions and you look at them, it's not so clear how they're related, but it's going to be very clear through the joint version, because essentially what we're going to have is just a flipped version of what we defined above. So we'll have the expectation over the joint distribution capital pi, and we'll have f of this time sigma k plus 1, because remember f is in ck plus 1. It's a function on k plus 1 faces, given that sigma k is equal to tau, right? So literally all I've done is I've flipped k and k plus 1. So in this one, we kind of we lift by averaging down, and in the down operator, you know, if we draw out the same diagram again, we have xk here and xk plus 1 here. Now we're fixing a k face, and we're kind of averaging up over the link of this k face. This is kind of like x tau. So now we're fixing a face tau, and then we're conditionally drawing a k plus 1 face, given that our k face is tau, and we're averaging over those values. So what's the explicit form? Maybe it'll be helpful to see the explicit form to understand what I'm talking about here. Well, okay, this will be equal to what? Well, I've said that you can think about it as summing over the link, level 1 of the link of tau, right? So we kind of know how to do that. So this is the sum over all sigma that contain tau, where sigma of psi is of size k plus 1. And so what are the probabilities in the link? Well, it's pi tau 1 of sigma without tau times f of sigma. And then remember that kind of by the way we defined probabilities on links, we can kind of roll this out with a normalization factor and just the standard probability on pi k plus 1. So this is equal to what? Well, a normalization factor given by the link. So pi k plus 1 x tau. So that's kind of all the weight that's on the k plus 1 level of the link of tau, which is, you know, just this thing I've drawn here in the diagram. And then we'll have the sum, again, over all sigma that contain tau, where sigma is at level k plus 1, of what? Well, now we're just going to have pi k plus 1 sigma f of sigma. So we could maybe simplify this further by expanding out this kind of shorthand normalization term here. But in general, I find that this is actually kind of the easiest explicit version of the down operator to work with. So again, I mean, maybe all of this math is confusing, but remember back on the diagram, really all this is you fix a k face, you look up at all the things that contain the k face, and you average over them. The only difference is that the averages are now weighted. It's not uniform, right? The averages are actually weighted by our distribution on the complex. And the way of kind of formalizing this, or one way of formalizing this, is by defining it with respect to this joint distribution out front. Okay, so I only have 4 minutes, so I probably don't actually have time to go through the next claim, which is that these are adjoint matrices. And in this claim, you'll see why it's super useful to define them in terms of the joint distribution. So maybe I should just pause and kind of ask, since this is a very important definition, the up and down operators we're going to be using for the rest of the class. Maybe we'll just pause here and see if there are any questions about them, and then we'll pick up kind of next lecture using these to formally define the higher order random walks and using that to give the extension of random walk expansion to complexes.
Let me just make one comment. Because to me, at least, it's somewhat confusing why, you know, this UK is just this nice average of a f of sigma, while, you know, the down operators use this weird pi, you know, coefficient. So maybe I should give one example. I mean, imagine that you have a graph, right? But it's not a regular graph anymore. So some nodes have large degree, some nodes have low degree. And really, pi1, there's a pi2 is just the edges. But pi1 will just be the stationary distribution of the nodes, which now will not be the uniform distribution anymore. So it'll be some other distribution depending on the degrees of the nodes. And then what are these two walks? So the up walk basically says, well, go from a node to an edge, but it really is, as a random walk, walks in the reverse direction. So given an edge, you choose one of the two nodes, randomly, and then it doesn't really matter what is the weight of the edge, right? It's irrelevant. You have an edge, here's two endpoints, choose one of them random. While the other direction, the reverse direction, is you start at a node, you want to go to one of its edges, especially one of its neighbors, and then it depends. The stationary distribution suddenly matters, right? So that actually this is the random walk corresponding to the graph. Yeah, and again, I don't know, at least to me, this is some explanation why, the formulas that when you write them out, they look different. But really, like Max said, probably the best way of understanding it is just this conditional distributions. You want to choose a node and an edge jointly. And then you ask him, if you want to go for the operator, you're going to condition on the edge and ask what the node is. And if you want to go on the down operator, you're going to condition on the node and ask what the edge is. But really, the important distribution is this joint distribution of nodes and edges. Anyway, that was just my 2 cents on that.
Yeah, I think that's a nice intuitive way to view things. Another maybe less intuitive but more formal way to view, why is the up operator this really nice thing that doesn't contain pi, but the down operator contains pi, is to remember that kind of the up operator is averaging down, right? Like Shahar said, you're fixing a k+1 face, and then you're looking kind of down at k faces. I remember that the way that we inductively defined the distribution pi was top down, right? So how do we get a k face? You just pick something uniformly at random from a k+1 face. So when we're averaging down in the complex, kind of how by formality, by how we defined this distribution on the complex, moving down will always be nice and uniform, right? Because the way that we move down is we pick something from pi d, and then we just choose something uniformly at random. So the way that we defined pi basically is inductively moving down. So whenever we move down, things are nice. But then when we want to move up, right, when you define things uniformly down, up isn't necessarily so nice, right? If we then fix a k face and we want to ask, well, what's the probability of some k+1 face with a fixed k face? It's no longer a uniform down thing. You kind of have to look at, oh, well, what was the probability of all these, k+1 faces, and things get more complicated because you didn't define it inductively up, you defined it inductively down. And so there's some difference in down is kind of the natural direction, and up you need to account for all these differences in probabilities. Shahar's way is probably a bit more intuitive, but at least in terms of the definitions, this is why you see this major difference. Okay, so I guess we're out of time. I'll stick around for questions. Shahar can say more.
Yeah. Just one thing. I mean, I think it's good for everybody. These are like somewhat unintuitive definitions. And the first time you view them, maybe nothing just later. It's good that you work out the calculations. That you convince yourselves why the things work. I mean, and why these are actually the analogs of what we've seen for like the node edge, node walk in the graph case, which is maybe more intuitive. I think it will be very, very instructive for all of you to do these calculations for yourself, so internalize these definitions.
I also highly recommend that when you think about these, to always kind of go back to the diagram view we had where you write out the poset and you look at a specific level and you then either average down or average down or average up. And that kind of in the end, that's all that's going on. There are some different weightings, depends on the distribution, but really all you're doing is you're pictorially on this diagram and you either want to look up or you want to look down. That's really all that's going on, up to weighting factors. Okay, so should we wrap up for today? If there are no more questions?
Yes, either everything is clear or nothing is clear. Okay, I guess we'll see you all next time.
Yeah, next time we'll see. I think it'll also help to see some examples of using these things, which we'll get next time.
Definitely, yeah.
Thanks.
All right. Bye, everybody.
Thanks.